And finally, after limits and continuity, now we get to the derivative. In this lecture, we are going to talk about the partial derivative, which is derivatives for multivariable functions. Let's do a quick recap. When we have a single variable function, f of x, if you remember from your Calculus 1 course, we define the derivative as the slope of the tangent line. And we get to the tangent line by taking 2 points from the function. That will give us a secant line. Then we bring one of the point really close to the first point. Then the secant line will change its slope, and when it is really close to the first point, then the line connecting these 2 points is the tangent line. And to find the slope, we take the increment in y over the increment in x. And suppose we call the increment in x as h. Then the derivative of the function, by the definition, that is the limit as the increment h approaches to 0 of increment in y, that is f of x plus h minus f of x over the increment in x, which is the h. How about if we have a function that has 2 variables, f of x and y? Let's let the output be c. So c equals to f of x and y. Then what is the derivative of f at a and b? Since we have 2 variables here, so to find the derivative, we have to fix one of the variable. For example, if I fix x, then the function c becomes f of a and y, where a is a constant, the coordinate of the point. So now the function c is function of y only. Then we can find the derivative of this function using what we learned from Calculus 1. That would be the limit as h approaches to 0. And now we fix the first coordinate as a constant, so we have a. In the y coordinate, I have b plus h, then minus f of a and b, divided by the increment in y, that is h. And the notation is f sub y at a and b. And we call this the partial derivative of f with respect to y at a and b. Similarly, we can fix y. If I fix y, then the function becomes f of x and b. So the b is the constant, the y coordinates of the point. So now the function is function of x only. So I can use our definition of derivative from Calculus 1. So I get the limit as h approaches to 0 of the function evaluated at a plus h, and I fix my y, so y coordinate is b, then minus f of a and b, then divided by increment in x, which is h. And we denote the derivative of this as f sub x at a and b. And we call this the partial derivative of f with respect to x at a and b. We can generalize the derivatives. So not only the derivative at a and b, we can get the partial derivative function. So if we want to find the partial derivative of the function f with respect to x and y, then that would be these 2 limits. For the first one, we have partial derivative with respect to x. That means we are fixing y as the constant. And the second one, it is the partial derivative with respect to y. So now we are fixing x as constant. And below, it shows different notations for partial derivatives. We've seen the first one, f sub x. We can also, for short, now writing the coordinates x and y, so we can rewrite that as this. Another notation is using df over dx, but to denote that the function is a multivariable function, and we are using the partial derivative. Instead of the full derivative, the d, now we have the partial derivative. So it's similar to d, but the top is folded. Or we can think this part as an operation. So we write the partial derivative of the partial derivative with respect to x, and the input for this operation is the function f of x and y. Or we write the function as what we define the c, so the partial of c with respect to x, or f sub 1 for the first variable of the function, which is the x. Or we can write that as d sub 1 of f, or d sub x of f. And the same thing for the other variable, the y. Above we've talked about the partial derivative in terms of the limit, but how do we actually find the partial derivatives? If we want to find the partial derivative of f with respect to x, then we treat y as a constant, and we use the same derivative rules that we learned from Calculus 1. So we differentiate the function f of x and y with respect to x by treating y as a constant. Similarly, the partial derivative with respect to y, we are going to treat x as a constant and use the same derivative rules that we learned in Calculus 1. Now let's look at some examples of partial derivatives. The first one, if the function is a two-variable function and the rule is x cubed plus x squared times y cubed minus 2 times y squared. Let's find the partial derivative of the function with respect to x and y evaluated at 2 and 1. Let's first find the partial derivative with respect to the two variables. The first one with respect to x. So we are going to treat y as a constant. Then the first term, derivative of x cubed, that would be 3 times x squared, then plus, the second term is x squared times y cubed. But we are going to treat y cubed as the constant. So you can think the second term as some constant a times x squared. Then what would be the derivative of that? That would be 2 times x times the constant a. Then we replace the a back. So we get 2 times x times the constant y cubed. Then the third term, we have negative of 2 times y squared. But since y is a constant, so whole thing, the third term, 2 times y squared is a constant. And derivative of a constant is 0. So the third term is 0 for the partial derivative with respect to x. Then to find the partial derivative with respect to x evaluated at 2 and 1, then we simply need to substitute x by 2 and y by 1. Partial with respect to x at 2 and 1 equals 3 times 2 squared plus 2 times 1 cubed. The first term is 3 times 4, that's 12, then plus 2 times 2, that's 4. And 12 plus 4 equals to 16. How about with respect to y? Let's first find the function. So the partial with respect to y, we are going to treat x as a constant. So the first term, x cubed. If we treat x as a constant, then the first term is a constant, and the derivative of a constant is 0. Then the second term we have x squared times y cubed. But x squared is a constant here. So we can think the second term as some constant c times y cubed. So its derivative would be 3 times y squared times the constant c. Then we substitute the x squared back. Then we get 3 times x squared times y squared. And the last term, this term only has the y, so its derivative is simple. That would be negative of 4 times y. Then we substitute x equals to 2 and y equals to 1 into this derivative function. So partial with respect to y at 2 and 1 equals 3 times 2 squared times 1 squared, then minus 4 times 1. That is 12 minus 4, and that equals to 8. So note that even though we are taking the first derivative, but with respect to different variables, we get to different values, even we are evaluating the partial derivative at the same point. Here we found that if it's with respect to x, we get that the partial derivative equals to 16 at 2 and 1. But if we are taking the partial derivative with respect to y, we get 8 evaluated at the same point, 2 and 1. How about the second example? If the function is e to the power of x squared times y, find the partial derivative with respect to x and y. Let's start with the first one, with respect to x. So we are going to treat y as a constant. Then the function is e to the power of some constant times x squared. Now we have to use the chain rule since in the power we have some constant times x squared. That is a function of x. So by using the chain rule, that equals to the derivative of the other function. e to the power of x squared times y, then multiply this by the derivative of the inner function. And here we still need the partial derivative, since the exponent is a function of x and y. So multiply by the partial derivative of x squared times y with respect to x. So we are going to treat the y as constant. Then the partial derivative of this will be 2 times x times the constant y. So this equals 2 times x times y, then times e to the power of x squared times y. How about with respect to y? So now we are going to treat x as a constant. Similarly, we'll need to use the chain rule. The derivative of the outer function is the same, e to the power of x squared times y, then multiply by the partial derivative of the inner function with respect to y. So the latter part, we have the partial derivative of some constant, which is the x squared, times the variable y, and derivative of y equals to 1. So this equals the constant x squared, then times e to the power of x squared times y. Let's look at one last example. Here this function is a function of 3 variables, x, y, and z, and the rule is 2 times x to the power of x times y squared times z. We want to find the partial derivative of the function with respect to x, y, and z. Let's start with the first one. If we differentiate the function with respect to x, then I'm going to treat the other variables, the y and z, as constant. So my function becomes 2 times x to the power of x times some constant. I have the variable x in the base, also in the exponent. So to find this derivative, I need to use the log differentiation. I can take the line on both sides. The left-hand side would be line of f, and the right-hand side would be line of 2x, and this to the power of x times y squared times z. Then I use the property of line. I can bring the exponent to the front of line. So this also equals x times y squared times z times line of 2x. Then I take the partial derivative with respect to x on both sides. On the left, since the function f is also a function of x, so I need to use the chain rule on the f. Then the partial derivative of the left-hand side would be 1 over f, the derivative for a line function. Then multiply this by the partial derivative of the inner function, which is the partial derivative of f with respect to x. And this equals the partial derivative of the right-hand side. And I'm going to treat the y squared times z as a constant. So I have the variable x times line of 2x. Then I'll need to use the product rule. I can first factor out the constant y squared times z, then find the partial derivative with respect to x of x times line of 2x. Then I expand the partial derivative using the product rule. So this equals y squared times z, then times derivative of x is 1, so line of 2x plus x times derivative of line of 2x. That would be 1 over 2x, and using the chain rule, I still need to multiply by the derivative of 2x. That would be 2. I can cancel out the 2x in the denominator by this 2 and this x. So this equals y squared times z times line of 2x plus 1. Then I can solve for the partial derivative of f with respect to x by multiplying the function f on both sides. That is f of x, y, and z times the right-hand side, y squared times z times line of 2x plus 1. Then I substitute my original function, f of x, y, and z, back to this function. So the partial derivative with respect to x equals 2x to the power of x times y squared times c, then times y squared times c times line of 2x plus 1. For the other two partial derivatives, they will be easier, since the variables y and c, they only appear in the exponent. And if you remember from your Calculus 1 course, we know the derivative of an exponential function with any base b. So the derivative of b to the power of some function of x, it would be b to the power of u of x times line of b, then times derivative of the inner function, which is u prime. So we're going to use this to find the partial derivative with respect to y and c. If it is with respect to y, then we are going to treat x and c as constants. So the base 2x is the constant, and the exponent is some constant times y squared. So using this derivative formula, we get the base 2x to the power of the original inner function, x times y squared times c, then times line of b, which is line of 2x. Then multiply this by the partial derivative of the exponent with respect to y. That is the partial derivative with respect to y of x times y squared times c. So this equals the partial derivative of x times y squared times c will be 2 times x times y times c, and the rest remains the same. So 2x to the power of x times y squared times c times line of 2x. Similarly, for partial derivative with respect to z. So the first two terms remain the same, since c only appears in the exponent. So we have the base 2x, which is a constant, to the power of the inner function, x times y squared times c, then times line of the base 2x, then multiply this by the partial derivative with respect to c of x times y squared times c. And the partial derivative of the third term, if we treat x times y squared as constant, then the derivative of c is just 1. So we get x times y squared times, the remaining is the same, 2x to the power of x times y squared times c, and times line of 2x. And that is the end of the lecture. In the next lecture, let's talk about the interpretation of partial derivatives.